So, um, if a robotic surgical arm misses its target by like a fraction of a millimeter, I mean, the result is catastrophic, but preventing that disaster doesn't actually start in the operating room.
Right. It starts way before that.
Exactly. It starts with raw chunks of metal and just incredibly violent heavy machinery. So, welcome to today's deep dive. Our mission today is to unpack this highly technical slide deck we found. It covers precision power transmission vocabulary, and we're going to trace how raw steel becomes these flawless, zero-tolerance systems powering our automated world.
Yeah, it's a journey from basically brute force to, microscopic refinement. I mean, you can't just cast a perfect gear. You really have to torture it into shape.
Which brings us to the rough cuts, right?
Yeah.
It's kind of like high-end woodworking. First, you use heavy saws to create the basic shape. Then you use fine sandpaper for the perfect fitment. And finally, you assemble the pieces so the door doesn't squeak.
That's a really great analogy.
So, starting with the heavy saws of the metal world, the slide deck focuses heavily on two primary methods, gear hobbing and internal broaching. And hobbing is fascinating because of the mechanism.
Oh, for sure. It spins a cutting tool in perfect synchronization with the gear blank. It's almost like two gears already turning together, carving the teeth out in one continuous flowing motion.
Right.
And that continuous generation makes it ideal for mass-producing sun and planet gears.
But for the internal wing gear housings, manufacturers switch to internal broaching, right? Like instead of continuous carving, broaching cuts those internal gear teeth in a single massive forceful pass. Which, okay, let's unpack this.
Yeah, go ahead.
If broaching happens in just one single stroke, doesn't that massive force risk tearing up the entire piece? I mean, compared to the continuous nature of hobbing, if something goes slightly wrong?
Well, what's fascinating here is the brilliance of the broaching tool's geometry. It's engineered with a series of progressively larger teeth along its shaft.
Oh,
Yeah, so while it looks like one brute force stroke, it's actually a highly orchestrated sequence of microscopic cuts happening in milliseconds. You get incredibly high consistency and massive throughput.
which establishes the baseline geometry of the gear.
Exact.
But establishing that shape is only half the battle. Because to survive industrial loads, those freshly cut gears have to be hardened through intense heat treatments. And as any mechanical engineer knows, introducing extreme heat warps metal.
Right, and that heat distortion is the absolute enemy of the tolerances we're aiming for. A warped gear simply cannot function in high-end robotics.
So you can't build high-precision systems with warped parts.
No, not at all. Manufacturers have to deploy gear grinding to recover that lost precision. They use these abrasive grinding wheels to shave away the microscopic imperfections left behind by the forge.
Going back to the woodworking analogy, it's like taking a finely honed diamond wheel to a rough-cut gemstone, or sanding down a warped wooden door after it's been left out in the heat, just ensuring it clicks shut perfectly.
That's spot on. You aren't changing the fundamental shape anymore. You're just hunting for absolute geometric perfection. In practice, this step is non-negotiable for components like the cycloidal discs used in robot joints.
Wow.
Yeah, if you skip grinding, the joint operates with a clunky, jerky motion that just destroys its own utility.
But a perfectly ground gear is still just a paperweight until it meshes perfectly with another gear when assembled.
Right, system alignment is everything.
And the deck talks about backlash, which is the empty clearance between the non-working mating surfaces of the gear teeth. And for high-precision systems, that backlash has to be practically non-existent.
Zero backlash is the holy grail. The slide deck points out that harmonic reducers achieve this near-zero backlash state by actually utilizing elastic deformation.
Okay, here's where it gets really interesting. If harmonic reducers rely on elastic deformation to kill the backlash, aren't they basically bending the metal to fit?
Basically, yes.
Does that impact durability? Like, wouldn't that constant flexing totally compromise the metal over time?
Well, if we connect this to the bigger picture, it would, if it exceeded the material's limits. But this deformation is engineered strictly at a microscopic scale, well within the metal's natural elastic limit.
Oh, I see.
Yeah, so it flexes and bounces back without permanent fatigue. And that reliance on precise deformation relies heavily on concentricity, ensuring the rotational axes across all these circular features align flawlessly.
Right, because concentricity isn't just about centering. It's about preventing a planetary gear system from literally tearing itself apart because one axis is like a fraction of a millimeter off.
Exactly. That's the fatal flaw. If you have zero backlash but poor concentricity, the loads distribute unevenly, the mechanical stress spikes, and the system shreds itself.
It's such an incredible engineering pipeline. We go from the aggressive synchronized cutting of hobbing and broaching to shaving off heat warps with grinding, down to managing the invisible physics of backlash and concentricity.
It really is. The automation you rely on is entirely built on mastering these microscopic realities. Without them, modern machinery simply cannot function.
Which leaves you with an interesting variable to think about.
Yeah.
We've mastered these incredibly tight tolerances here on Earth. But think about what happens when we start putting these highly engineered robotic systems in deep space or extreme environments.
Oh, yeah. That changes everything.
Right, where dramatic temperature swings completely alter standard metal elasticity. How will we conquer backlash and concentricity when the physical rules of the metal itself start changing? Something to mull over until next time.